Welcome to fine-tuning the Code Llama LLM with weights and biases. Today we'll be discussing the traditional machine learning model lifecycle. And so from a machine learning workflow perspective, that usually involves a training dataset sourced from your data platform like Snowflake, a pre-trained model sourced from a platform such as Hugging Face, and together they're combined via a process called fine-tuning, where resultant model is then evaluated, documented, and deployed for whatever your use case and your dataset was specified for. So you have an ML model that has been built by an ML practitioner, passed over to an ML ops engineer to ensure that they are properly scaled with the correct infrastructure, and then an ML team leader who ensures the success criteria of this ML model for whatever the deployment was used for. And so for each of these personas and steps, we have a different collection of software tools tailored for each of these users. And so this software stack, while reminiscent of a traditional software stack, tend to look a little more specific from an ML perspective. And I'll walk through that what that looks like later. So before we get into any of the demo, we'll first talk about why we care about a model such as Llama 2. Then we'll talk about how Code Llama 2 differs from Llama 2 and why it exists. Then we'll think about when comes the opportunity for us to fine-tune these large language models, specifically for our data sets and use cases. And lastly, we'll actually run through that process through a collab and a couple dashboards. So first, let's talk about Llama 2. Llama 2 is a collection of pre-trained and fine-tuned large language models released by Meta. They range from 7 billion to 70 billion parameters, so existing on the higher end of the large language model space, but not as large as some models that tend to hit the hundreds of billions to the trillions of parameters. However, it is an extremely effective model and has been fine-tuned to also incorporate a chat perspective that makes it more realistic from a human response criteria. And so that process is called reinforcement learning human feedback. So there's a step involved creating Llama 2 via pre-training, and then a fine-tuning step using that technique I mentioned to ensure it actually sounds like a human and does not give any improper responses. And so quickly to touch on RLHF, or reinforcement learning human feedback, it exists for the precision, contextual appropriateness, and ethically aligned responses from our large language model. And so this usually involves taking a human annotator who judges the responses from these large language models and ensures that when in our training process, we always ensure that our model selects the most human response. And so that is trained from a model that was used by these judge scores by these annotators. And so to take it one step further, we take this Llama 2 chat model, which has more human-like responses, and we actually fine-tune it even further so that it's very specific to responding to code-based questions in a response very similar to like a Stack Overflow. So this is very useful as this takes our Llama 2 model and allows us to provide instructions such that it will help us respond to code-based queries. And this is useful from a code writing, completion, and debugging perspective across all programming languages, but most popularly Python, C++, and Java. So now we've touched about Code Llama and Llama 2, let's think about when to and why we need to fine-tune LLMs, such as Llama. And so we can see here from this image that there are a variety of use cases that revolve around fine-tuning these types of pre-trained models. And so just to do a quick recap of fine-tuning, that's when we take a pre-trained model, which was trained on a generic data set, we provide very specific data that is involved with the task that we want this data to solve. So in this case, we will be fine-tuning on our medical data for the task of writing a diagnosis from a given report that is reminiscent of that medical data that we passed in. However, traditionally, we see that adjusting, so in these models, there tends to be a lot of parameters, as we mentioned. So from 7 billion to 70 billion are the number of parameters that all need to be updated during this fine-tuning process if you're adjusting all parameters. In the traditional ML world, only adjusting a few amount of those parameters tends to result in what we call maybe not a best model. However, in the scale of these large language models, a lot of research has been done on the concept of parameter efficient fine-tuning, such as techniques such as low rank adaptation or LoRa. And these involve selecting a very specific subset of parameters within our model and choosing to fine-tune on that. And so effectively, from a perspective that we care about as these fine-tuners, it's extremely quick and efficient to use these parameter efficient techniques. It allows us to reduce the volume of data and the amount of computation needed to actually train these models, as we no longer have to update every single parameter. And instead, we can focus on only updating a smaller amount of parameters, allowing us to use smaller GPU resources and still get the same degree of efficacy as the full parameter updates. And so now that we've touched on the topics of Llama 2, Code Llama, when and why to fine-tune large language models, let's actually go ahead and fine-tune Code Llama for a very specific use case. So, as we all know, GPT is a very popular and powerful tool. So on our end, we have actually used LLMs and GPT-like tooling to create WanBot, a chatbot selected specifically to respond to user queries about our package, weights and biases. And so from a high-level architecture perspective, this involves a couple steps. This is a process called retrieval augmented generation, which I will not touch upon in this talk. However, the important thing here to mention is that in essence, we are having a collection of standard software tools that coalesce together into a prompt. And this prompt will contain things such as context relevant to the user query, and then the specific instructions that we want to provide to our large language model to ensure a consistent and correct output. And so as we create this chatbot and have this process of our bot communicating to our users, we also ensure that we have this feedback loop provided to us. And so when users provide this feedback, we are able to coalesce all of these tracked questions and the quality of the response to these questions into one location. So we use Snowflake for this situation. And so using this data set of user question pairs alongside the feedback hosted on Snowflake, we will fine-tune Code Llama using Hugging Face, the framework, and having all of the analytics regarding the model training centralized in the system of record that is weights and biases. We will then take that final fine-tuned model and evaluate its performance. So let's do that now. So first, to take a look at our data set, we see there's a collection of columns relevant to us, be it answer, context, question, and text being the combined form of that question, context, and answer. We've also beforehand filtered this down to all of the responses that were thumbs up, aka were given a positive user feedback by users, as we want those positive user feedback to be the representative data that we're fine-tuning on. So as the first step of our process, what we'll do is we'll connect to our Snowflake database. And then we'll initialize a weights and biases run, a single unit of computation that will automatically keep track of any system metrics regarding CPU and GPU usage alongside any other data that we want to stream to our dashboard or analytics. And so in this case, what we're doing is we're actually going to perform a transform on the data coming in from Snowflake, coming down, materialize into a data frame format, and then we'll be creating the new column, which will contain all of the data in the proper format for the large language model that we want to train. So in this case, we define the delimiters for instruction, system message, and end of sentence. We provide some instruction about the behavior of the chatbot, and then the context, question, and ideal answer from the positive user feedback. So with that as our data set, what we'll essentially do is perform that transform and save our data set after tokenization and chunking into a format that is ideal for usage with these training platforms such as Hugging Face. And so in this case, we want to pre-partition our data such that it can be easily ingested without any other further transform into our training process. And so what we can do is, after saving it in this format, we can save this within our artifacts offering within weights and biases, which is essentially a bucket which can save any blob of data that you want to send to it. And it also comes with automatic version tracking and the ability to create explicit lineages between steps of these units of computation called runs. So the reason I mentioned that is now we can directly and explicitly link which version of training data touched which version of training for our deployed models. And I'll show that to you later. So now that we've performed this transforms and saved our data set into our artifact, we essentially condense our training data set also into a new data frame specific for evaluation. So in this case, it is the same prompt, but we're obfuscating the answer as we want to be able to analyze the generator response from the LLM given that it doesn't know the answer already. And so similarly, we chunk that data set and also save that within weights and biases as an artifact. So now that we have all of our data saved and properly formed into an artifact, we also save a sample of each of the data set to be viewable and analyzed within weights and biases itself via our tables offering. So to actually look directly at what that looks like within a dashboard, you can see here that we have a page. And in this page, we have details about who ran this specific experiment, any details about the system itself and where it was run on, any configurations if they were defined, and in this case, there were none. In this case, I also have artifact saving on and code saving on. So as I spam the save button within Colab, it saves that every version of that within my workspace. And alongside, you get all the charts regarding system utilization, logs, and any underlying files that you have generated during the creation of this process that you explicitly log here. But the one thing I do want to mention is actually this data set. We can see here we actually have our questions saved in the efficient format needed by Hugging Face. Similarly, we also have every version of the data as we made changes to it. So in this case, we know we took this text formatting run and created this questions data set. In this case, we also tokenized our data set and created this tokenized data set that originally came from questions. And similarly over here, we don't explicitly link the training data set that we get it from, but you'll see where this specific evaluation data set generated from and all the underlying details surrounding that, be it from time or from system information. Now that we created the data set that's proper for training and fine-tuning our large language model, we can go ahead and actually start performing training. We can go ahead and first load in that tokenized data set from the previous step that I've shown in our dashboard. Then we define a configuration for all the different components we care about when training this large language model. So in this case, I'll leave this here for you guys to read and pause. And after that, we take our data set already pre-formatted properly for Hugging Face training and ensure that we split the data set into train and test as we wanted to perform validation during the training process. Then we load in the model that we care about. So from our configuration, we can see this is the Code Llama model that you must accept the license form from Hugging Face. Now that the model gets loaded in from Hugging Face, we can go ahead and perform some specific instructions about how we want this information to be processed from a data set and from a training perspective from the trainer that will actually provide the training interface between the model and the data set. These are all fairly standard configurations that are set during the training process. So I'll leave this here for you to investigate on your own. I do want to mention, though, that the evaluation steps, for instance, and the logging steps are very important to us, as this defines the amount of times that we want to save our information for analytical purposes during our training process. And for demonstrative reasons, I left this as epoch 1. And so I'll show you what a longer run will also look like from one of my colleagues, as these are very collaborative dashboards. So from beforehand, as I mentioned with parameter efficient fine tuning versus full fine tuning, If we were to fine tune our model naively, we'd have to update all 6.7 billion-ish parameters. However, because we're using parameter efficient fine tuning and only selecting a specific subset of underlying modules and or layers from our original LLM and saying that we're only going to update those small volume of parameters, that means the amount of data and process needed during each step of backpropagation will be a lot less compute intensive due to the smaller volume of parameters that actually need to be updated. So now that we are able to actually freeze the model itself and reduce the parameter count, we can define some behavior regarding how we compute accuracy. And then we can provide all that information into the Hugging Face trainer, where we've defined the model, the training arguments, our training and evaluation dataset pre-formatted from the previous step coming from our Snowflake database, any definitions regarding how we want to collate data, and also provide metrics such as evaluation accuracy. So now that all that information has been defined and configured, we can pass this information to the Hugging Face trainer, which will then utilize our WANDB callback. But in our case, we actually want to define some extra behavior that the traditional WANDB callback doesn't provide, as the traditional WANDB callback already provides automatic logging of hyperparameters, metrics, and checkpoints if defined. We actually want to build even more on top of it. And so our SDK and Hugging Face make this extremely easy. So in this case, we define some information about the behavior on whenever evaluation runs, and we define this custom behavior. For us, this custom behavior is essentially, we want to take the response from the large language model and ensure that we save it during each update of evaluation so that we can see how well the model is actually improving on qualitatively by actually looking at the generation itself, as opposed to using some sort of other measure that may not actually grab the semantics of the response that we care about for this code generation piece. So now that we've defined our new callback, we can explicitly say, hey, trainer that we defined earlier, let's add this callback in, which now during every evaluation step will add in these additional rows to our table that we want to use for analytical purposes, but also the same behavior of hyperparameter logging, metric logging, and checkpoint logging if we so want it. In this case, we turned off checkpoint logging. And training is as simple as calling trainer.train once you've put all the pieces together of the dataset configurations and any useful callbacks. As you're training your large language model, you'll see that all of your metrics and hyperparameters are being streamed directly to your weights and biases dashboard. So not only will you see measures such as your evaluation metrics and your training metrics, you'll also be able to see things such as your GPU utilization maxed out at 100%, hopefully, an overview of all of the system information I showed earlier, but in this case, we also get to see the full breadth of configuration that went into the construction of this specific model itself, and be able to easily pull that and audit that ourselves whenever it comes need be for our analytical process. And also, we're able to see any other resultant information saved and used in this case. So like for instance, in this training run, we can see that if we were able to go back to this lineage, that this dataset was used for a variety of training runs. And so this is really nice to see as we're able to understand if there were any problems with any one of these models, we can isolate whether it was a dataset problem or if it was specifically a problem from that training process itself. More than that, as we start to run a collection of experiments, we can actually centralize them in a comparative fashion in one dashboard here. So you can see that not only are we getting all of these evaluation generations coming in as we defined in our custom callback, we're able to actually go ahead and compare these across different models. So not only look at metrics across different experiments in one view, but also be able to compare the quality of generations over the evaluation process between different models. So in this case, I can see that Cosmic Snowflake 11 is the green color here. So I can turn off Cosmic Snowflake and we get a better look at Fiery Vortex and be able to then compare, did I like the generations of Cosmic Snowflake 11 more or Fiery Vortex 10? And so all this is always serialized and saved in this one location. So if at any point you are happy with the charts that you see here, you can take all this information and add it in to a collaborative system called reports. So in this case, I'm going to make a new report, which will be used to share evaluation over my new Code Llama run. And publishing this project means as easy as sharing a single link to real-time and updated dashboards of any selected metrics that you find valuable to share with a stakeholder. So now that we have our training process finished, we can actually go ahead and run evaluation very directly. So skipping over a lot of the information here, loading in a model is as simple as pointing to the location of your saved model. So in this case, we have a specific folder called here Code Llama 7. We load in that model via the same process we did earlier via Hugging Face when we defined it from the traditional Code Llama URL. And instead, we define some behavior to run generation. So instead of running through this, it's as simple as seeing, hey, generate a new sample of generation given the text from my evaluation data set. So another form of being able to, after training, check the final outputs from our model. But one thing I do want to highlight here is how slow this process actually is right now. The problem here is that because we're using the finally fully loaded in model, it is a lot slower than using a very optimized framework, which I'll show you next. Regardless, we're able to take all of the generations from our training process, store them into another weights and biases table, and go in and we can actually look at the generations themselves. So here we can see that from one of my colleagues' collection of experiments regarding fine-tuning, we can go in and see his collection of different tables generated. And let's look at his degree of generations down here. So you can see that similar to what we saw during our generations during the training process itself, these are very similar. But we actually go in and actually expand the full context of this. I prefer Markdown to make it a little easier to read. And so we can look and investigate the input query given by a user quite easily, and then also see the generated response alongside any retrieved context. So using all this information, we can do a good qualitative analysis to understand what went wrong during this generation given the input query and the retrieved context, and be able to isolate whether or not it was a improper context that was passed to our prompt, for instance, or if it was something more related to our prompt itself, and allow you to keep iterating on and understanding which data set changes you need to make and what those changes may look like from a data set perspective. So, lastly, seeing as how long the original evaluation process took, we instead might opt to use a tool such as VLLM to provide a better interface for quick and an efficient generation and inference of our loaded model. And so what's really nice is VLLM plugs in quite easily with a Hugging Face. And then from our perspective, because in our previous step, we were able to explicitly save our model in this step here, which I did not point out over here. You can see that we explicitly save our model to weights and biases, so we can directly and easily retrieve that model and then use that model to go ahead and run VLLM, the VLLM inference server, which is significantly quicker and still has a very similar workflow as we saw in the evaluation process earlier, where from a weights and biases perspective, the table logging is straightforward, and the generation of the LLM has now been sampled to easily one line of code. Reduced to one line of code. And so from our perspective, looking at one of my colleagues' dashboards who used a slightly different GPU and ran it at significantly earlier time than me, we can see that his generations look very similar to the one we saw in the previous table. So this is very nice to see that we're able to use packages and frameworks that are optimized for this ML inference process, but still be able to use the tooling that we like to use, such as weights and biases and Hugging Face. So as a recap, we use a dataset of user question answer pairs hosted on our Snowflake data platform. We were able to pull this data down and perform standard data transforms to ensure that we're able to use this data set effectively for Code Llama trained using Hugging Face trainer. And then we took this Code Llama model that we fine-tuned and ran evaluation during the training process and after the fact to understand how well this model actually did from a qualitative and quantitative perspective. And as a recap, weights and biases helps provide all the different layers of tooling needed so that at any point in your modular ML workflow, when a need arises for a specific tool from an analytical or system of record perspective, weights and biases has a tool waiting for you to help you in this model building process. So I'd like to say thank you and hope you all spend the rest of your days building really cool projects. I'd love to hear what you guys make soon. Thank you.